In the last lesson, we looked at centripetal acceleration for an object undergoing uniform circular motion, and remember that that was acceleration towards the center. But we know that accelerations are caused by forces, and that must mean when an object is moving in a circular path, there is a force that's causing that. And that force is also directed towards the center. It is a center-pointing force, so we do call it centripetal force. And by Newton's second law, since net force equals mass times acceleration, if the only thing that we have is uniform circular motion, then the only acceleration we have is centripetal acceleration. And so we can say that the centripetal force, Fc, is equal to mass times acceleration, AC, centripetal acceleration. So we have this, Fc equals mass times centripetal acceleration. Now, all we're doing is we're naming the net force towards the center. We are not saying what causes it. This is a net force equation. Net centripetal force is equal to mass times centripetal acceleration. Centripetal force is not the name of an agent. It's not the thing that supplies the force. What supplies the force depends on what kind of thing we have moving in a circle. So if this is the ball on the end of a string, then the string is actually supplying the force, right? So if you take a ball and just wave it in a circle over your head, it's the tension in the string, Ft, that causes that thing to move in a circle. It's the force that causes the acceleration. Since that force is causing it to accelerate centripetally, we can say that Ft is equal to Fc, assuming no other forces act. Now, that also kind of gives rise to this misconception that students have that says that there is an outward pointing force on an object that's undergoing centripetal acceleration. Because you felt it, right? If you've ever spun something over your head, then you felt that pull of something that's trying to move away from you. But that's not the force that's causing the object to move in the circle. That's the result of Newton's third law, right? Because the ball is on the end of the string is pulling on the ball. Pulls it in this way. That's tension in the string. But because the ball is pulling on the string, or the string is pulling on the ball pulls backwards on the string. And so you have to exert a tension force, or a force against that pull. And so the string is pulling on you, which feels like an outward pull, because it is, but that force is acting on you, not on the ball. Right? So this tension force and this tension force are equal in size but opposite in direction and do not act on the same thing. The tension on this end of the string is pulling the ball in towards the center, causing centripetal acceleration. This is the force that you're exerting on the string to keep the whole thing from moving out. And in fact, if you let go of the string, it's not that this thing flies out this way, it just continues moving in a straight line path, because the speed is constant and the velocity is tangential. What I mean by that is the velocity is always tangent to the circle at any point, and Newton's first law tells us that an object's velocity remains constant unless an unbalanced force acts on it. Well, if we get rid of that force, that means this thing is just going to fly in a straight line in whatever direction it's pointing. Whereas if we continue to exert that force, it continues to move in a circle. Now, I said that Fc, centripetal force, is not the agent that causes the force. It's just the name of that force. And we can see that tension in a string can cause that force, but we can also have other things cause that force. When you drive around a corner on the highway, you go around this corner, your car wants to continue going that way. And we've had icy conditions, and you know if you take that corner too fast, that you might not turn, right? That's because there's not enough friction there. And so sometimes it's friction between the object and the surface that causes a centripetal force. Sometimes you have a string. Sometimes you could actually have a wall out there. If you've ever seen a hockey game, you know that the hockey rink has curved sides. And if the puck is going along this side of the wall, then it gets to this curve and the wall is actually exerting a force in on that hockey puck. That's a normal force. It's causing the centripetal force there that's causing it to move in a circular path. So there's lots of different things that can cause an object to move in a circle. And we call the force that acts towards the center the centripetal force, but we still have to identify the agent that causes that force.